All right, we're already starting a couple minutes late, which I apologize for, but welcome to Ground and Borehole Geophysics. Our first speaker is Alan Jones, so welcome, Alan.
Yeah, thank you very much. I'd like to thank the two conveners for the invitation to talk about the future of MT, and when they sent me the email, I was really excited. I thought, wow, that's easy. But in fact, it's not. It's very hard to think about the future of anything. So what I'm going to discuss with you is talk to you or to present to you is the current state of the art, where MT is at. And particularly, I'm going to focus the discussion on MT applied to mineral exploration. I'm not going to show you any examples of applications of MT, but there's a wonderful talk tomorrow by Joel Jansen at 11:30, and he will be giving examples, and I suggest you all try to attend that, please. So magnetotellurics has got various flavors, and it depends on the frequency of operation, and it depends on your depth of investigation, all the way from very high frequencies that actually use radio transmitters, so it's not really a natural source technique, right through to the very long periods looking down to very deep depths. And in fact, I personally have used MT from the 100-meter scale to the 1,000-kilometer scale. And the physics is all the same, the mathematics is the same, and the difference is mainly in the mag sensors. And so that defines for you what frequency range you're going to be operating in, which defines the depth of investigation. For mineral exploration, we're going to be looking at what we call audio magnetotellurics. We call it that because it's in the audio frequency range. And the sources for us are lightning storms, and these are global lightning storms. The energy either goes from the cloud up to the stratosphere or from the cloud down to the ground, and we mostly see, of course, cloud to ground energy. And that propagates around the world in the waveguide between the Earth's surface and the ionosphere, and it gives rise to these famous Schumann resonance frequencies. The fundamental frequency is just under 8 hertz, as you can see those frequencies on the right-hand side there. So a very, very, very brief history. It was proposed independently in Japan and Russia and France. But really, it was this paper by Louis Kenyard, a seismologist working for CGG, who published a paper in 1953 that really caused the method to take off in the 50s. And it was a very influential paper of those three because it was written in English, not in Japanese or Russian. And it was published in geophysics, so it's very widely read. And it led, particularly in the US, to people building instruments, and the first commercial application was geothermal energy exploration. This is MT in the early days, and I'm fortunate enough to have been involved in the early days. My first MT site I recorded in 1942 in equipment much like that on the left. The diagram on the right is from my own PhD thesis, and those are recorded by pen on paper, and I had to hand digitize those. And I consider myself very fortunate because I come from a time when I had to build my own equipment. I had to write my own digitizing code. I had to write my own processing code. I had to write my own modeling code. I had to modify a 2D forward modeling code. I had to write my own inversion code. And so I really got to know the whole breadth of the method. And I've tried to keep touch with the breadth of the method over the last 40 years. Students coming into the game these days, they can't do that. It's just too broad, and they have to specialize. And so this is where we were in the mid-late 70s, basically 1D inversions or interpretations. These are actually, it's a Monte Carlo type approach through those rather poor data, as you can see. And so it's hardly surprising that through the 60s, 70s, MT took a long time to become established and accepted. And I would like to say that we've come a long way since that time. And that occurred because of a huge quantum leap in everything that occurred, particularly late 80s, early 90s. So we now have excellent equipment. We now have robust time series processing codes. We now have analysis codes that can remove galvanic distortion. We have some very excellent publicly available 2D inversion codes and some 3D inversion codes. We have joint inversion algorithms appearing, and the growth of the method, certainly in an academic sense, can be measured by that chart which shows the number of papers published in magnetotellurics. It's now nearing 4,000, and you can see that the growth is becoming exponential. So in terms of equipment, we've got some wonderful equipment. There's pictures from a couple of manufacturers. They're very robust. They can operate from very cold temperatures to very hot temperatures, and I've worked at both of those, northern Canada in the winter and Botswana in the summer. The mag sensors are very good. You can get now some hybrid sensors that try to cover the whole frequency range, but often you might like to pick a sensor for your task. And the diagram on the right shows you the noise levels of various different sensors. You're basically trading off noise against eddy currents in the core. Multi-channel receivers now move into 32-bit, and we now have receivers that can record high frequencies and lower frequencies using 2 sets of coils at the same time, and this is wonderful, and I'll tell you why in a minute. We've got processing codes that really are able to use the modern robust methods, and here's an example of 8 different codes on the same data set. Those in blue are non-robust, and those in red are 3 robust codes, and you can see quite clearly that robust codes make a huge difference. And this we did in the late 80s, early 90s. We've got analysis codes that can remove and reduce effects of galvanic distortion, and then can test for internal compatibility of your data. By Hilbert transformation, your apparent resistivities and phases have to be compatible with one another. So you cannot fit some sort of polynomial through each of them independently. You've got to fit a physics-defined curve. And that plot shows you one problem we have in the mining game, and that is at frequencies of 1 to 3 kilohertz, and those are the first on the leftmost large error bars, we have what we call the AMT deadband. And the problem with that deadband is that those frequencies are the frequencies when you begin to first see a mineralized body at around 500 meters depths in the resistive Canadian shield. And MT has taken off now that exploration companies want to look deeper. Anything shallower than a couple hundred meters, of course, control source methods are far superior. But if you want to look deeper, it makes a lot more logistical sense to go to natural source methods. But we do have this problem. And this problem is caused by the difference between those 2 sources of the lightning stroke. On the left is a picture of a red sprite. That's energy going from the cloud up. And on the right is a typical lightning stroke from the cloud down. And you can see that those 2 actually have different frequency content. And they overlap at about the 1 to 5 kilohertz range. And so we have a natural signal low in that range. Also, this is exacerbated by the fact that during the daytime, solar ionization of the atmosphere causes a 2 to 3 orders of magnitude increase in conductivity. And so the electromagnetic source waves coming to you get much more heavily attenuated during the daytime. And on the left, you can see a spectra at 4 in the morning in red and a spectra at 5 in the afternoon in green. And you can see the orders of magnitude difference in the 2. And on the right, you can see some time series, and you can see the nighttime, and then suddenly, as soon as the sun rises, just after 6 o'clock, the energy completely attenuates. And so really, to get through this AMT deadband, you have to record AMT data at night. But that's often a bit, you know, it's counterintuitive, because you only need 15 minutes or 30 minutes of data. And so this is why these hybrid systems that record AMT and MT at the same time are very valuable, but it does mean you've got to have a lot of systems. You've got to be capitalized. Your crew has got to put out 10 systems a day and then pick them up and move them the next day. Okay, there we are. So just to come back to this problem, there's the data. We are developing techniques now, and I have one that uses a statistical robust method that will, in fact, use the fact that your Hilbert transform has got side lobes, so the phase at different frequencies affect the apparent resistivity at your dominant frequency and so on, and you can actually retrieve interpretable data from the prior data. So in terms of inversion, we've got some excellent 3D inversion codes. Some of these are proprietary, unfortunately. Some of them are in the public domain. And we can invert at quite reasonable levels. But if you want to do this within your lifetime, you have to have rather coarse gridding, right, compared to 2D. We're often doing 2D models at 400 by 200 cells, where you do 3D at much, much coarser cells than that. We've still got some work to do to understand 3D. We really moved into 2D from the late 80s to early 90s, and it's taken us 20 years to really understand 2D. And I would say we still don't properly know how to appraise resolution in 2D, and particularly because we're using linearized appraisals, which are incorrect for resistive units. Joint inversion is coming along, and here's an example that was actually showed yesterday in Colin Farquharson's talk, joint inversion by Max Morecamp of tomography, seismic tomography, MT, and gravity. And on the top are those data alone, and on the bottom are a joint inversion scheme. And so we're beginning to see these. But we do have a problem, as Max found when he tried to make his code available. Schlumberger came after him and said they had patent rights. And University of Leicester don't have the pockets to take on that patent challenge. And so, you know, this really is an impediment to development of a lot of joint inversion codes if you're going to have Schlumberger running after you. So I list in my abstract a number of places where there's been MT applied over the last 15 years. It's a very incomplete list. A lot of work remains confidential. And as I said, please listen to tomorrow's talk. So moving on to where we're going, Quo Vadimus, or where I hope we're going. As Niels Bohr said, prediction is very difficult, especially about the future. My feeling is that magnetotellurics is on the cusp. It's bubbling, and it's either going to break through or it's not. And it needs to become far more routinely adopted and far more routinely applied to solve mineral exploration problems. And we need to have the same leap forward in MT now that we had in the late 80s and 90s. And if we don't, I think it'll remain a sort of esoteric backwater EM method. And so here's a list of things that I think need to be done, and I'm going to go through these with you. I showed this list to Dennis Woods 2 days ago, and he said, well, that's all motherhood. I said, oh, thanks, Dennis. And in a way, he's right. He's very right, because it's damn obvious what we need to do. First of all, you know, I think in order for people to understand, it's generally for MT, but also for EM, we have to understand that it's not like seismics. Our parameter varies by orders of magnitude, and this introduces a whole host of advantages and disadvantages. And here I'm showing you the MT response in terms of apparent receiving phase of a 300 ohm-meter layer, 3 kilometers thick, over a conducting half space in red or resistive half space in blue, and you can see the apparent resistivity curve on top and the phase curve below. Now let's have a look at those, though, in terms of penetration depth. And the black curve here is the attenuation of the electric and magnetic fields for a 300 ohm-meter half space. But those other curves are the attenuation in a conducting half space in red and a resistive half space in blue. And the E field is solid line and the H field is dashed lines. And you can see that these attenuate very differently depending whether you've got a conductive or resistive half space. Now, what does this lead to? Well, if you take those apparent resistivity data that were sampled on a uniform log period scale, and you transform them to approximate depth, what you find is that, and here's a 300 ohm meter top layer down to 3 kilometers. What you find is that when you're going into a conductor, your fields, if you like, become arrested, so they slow down. And you can see we have a huge number of points sampling between 3 and 4 kilometers. In fact, we have 12 points. Whereas when you enter a resistor, the electromagnetic fields, if you like, speed up. And so we have 1 point sampling the 3 to 4 kilometer depth range. And this is the reason why electromagnetic methods have poor resolution of the base of a conductor top of a resistor, because we don't have enough samples in the frequency domain. We need better, cheaper equipment. MT is undercapitalized with far too few measurements. We need far higher station density. There's a number of these network type systems, starting with the EMAP from many years ago, MIMDAS, Titan 24, Orion 3D. They're all steps in the right direction. But for some anomalies, you need to record all components for most, not just a subset. One problem is, as I said to Glenn as I walked in, this cell phone cost $500. It's an older one now, but there's more technology in this than there is in an MT receiver. But 1 billion cell phones were sold in 2015, so I do think that MT needs to up its game. We need to produce a lot more systems at a lot cheaper price. And there's new and exciting magnetic sensor technologies emerging, and you'll see those at a number of booths, actually. And so I think MT surveys need to ramp up in scale hugely, and that's only going to be possible if the equipment becomes cheaper by an order of magnitude. Instead of 50,000 for a full MT station, we need to be in the region of 5. And then layout. Remember, when you're doing layout, you first do a survey design. Do you need all 5 components? And here's an example of where you do. And this is a model of the Kidd Creek deposit. On the left, you can see the schematic model, and on the right, you can see the electric and magnetic fields. Electric on top, magnetic on the bottom. The black is the half space value, and the red is with the anomaly. And it turns out for the Kidd Creek deposit that 74% of the anomalous response is in the magnetic field, and only 28% of the anomalous response is in the electric field. And in the TM mode, you've got no measurable response. So certainly when you're looking for subvertical, thin, conductive, mineralized bodies, you have to measure 5 components at every site. Know thy anomaly. If not, make all measurements. We need to be able to lay these systems out much quicker. Capacitive electrodes, shorter E-lines, triaxial stands for AMT coils, maybe different mag sensors that don't require burial, and there's a very nice 3-component mag sensor in the showroom that you can have a look at, but you do have to worry about motion noise. So maybe you could put motion sensors on those and remove the motion noise. This is what the oceanographers do all the time. MT surveys need to reduce cost, and the only way to do that is to reduce equipment cost and reduce layout time. But never, never, ever, never sacrifice quality for speed. And this is something I always have to bash into my students' heads. They think they could make crap recordings in the field and repair it in the office. You can't. Bad data is bad data. You need to get really good data in the field. Processing, we need better processing programs, and I showed you this before. We've got some ways. We've tried wavelet filtering on this. We've tried other methods. But besides that, we have problems like cow fence noise. Signal on the one on the left, you can see the cow fence noise from Ireland, and on the right, DC train noise. And the problem is the world is becoming more and more electrified, more and more noisy. It's getting more and more difficult to do MT, so we have to find solutions for these. And we've tried with both of these types of signals to determine good responses, and we were pretty unsuccessful. Distortion analysis, here are 2 sites, 2 magnetotelluric sites. For those of you in MT, focus on the red and green, red and green points. These are your off-diagonal terms. They're the ones that contain most of the information about the Earth. These 2 sites are 2 kilometers apart. There's no way we can model those yet. We have no technologies to be able to model something that's so dramatically different, 2 kilometers apart. Inversion, what we are doing a lot of is what's on the left, which is a rectilinear grid that's static, it's frequency independent, it doesn't change from the beginning of your inversion to the end of your inversion. It doesn't matter whether you've got conductors in there, so that the numerical stability is compromised now. And so what we need to move to is arbitrary shaped dynamic frequency dependent grids that change to ensure forward accuracy and to focus on anomalous regions. And Colin Farquharson gave a wonderful talk yesterday about this. So we have to move away from smooth models, particularly in the mineral game. We don't have smooth models. We have to move towards these geological or structural models. We need to fit all the data simultaneously. We have additional data, maybe elevation, geoid, and surface heat flow is not that important in mineral exploration, but in other games it is. Personally, I'm an advocate or a student of Tarantola. I do think that we have to be looking at probability density functions that fit our data. We have a model space that's acceptable, and we've become a bit lazy. We've found the smoothest model, so we've found one point in model space, and we think we're superior than anybody else. We found this model. Well, we're not. We've got to describe the model space. And I think we do need to start from a petrological description of the Earth. And I'll just quickly show you how this works in the mantle. Here in the mantle, we describe the mantle, the upper mantle, in terms of its major oxide chemistry, and we assign to it prior PDFs, and then we pick from those prior PDFs and build up a forward solution, test those against our observations, and accept the models that fit and reject those that don't, and redefine our sampling distributions. It's a modified Hastings and Monte Carlo scheme, and this allows us then to build up a whole family of acceptable models. And on the left, we have the velocities going down to 400 kilometers, and on the right, we have the resistivity and the water content in the lithospheric mantle. And what I'm showing here are two sets of models. The yellow is one that fits to a global misfit of 1, whereas the gold fits each individual data type to a misfit of 1. And this is often a problem when you're doing joint inversion, that you can underfit some data and overfit other data. You have to watch out for that. I'm almost done. Yeah. Mineral systems, we have to build a predictive mineral system. We don't really know how conductivity gets created and enhanced within a mineral system. I really would implore you to think about the regional context. We need to build the regional context, and this was emphasized by Cam yesterday. All world-class deposits, all tier 1 deposits lie above geophysical, geochemical anomalies in the lithospheric mantle. And here's an example actually from Olympic Dam that shows images down into the mantle of fluid pathways, where you've got obviously fluid pathways right up to Olympic Dam and to some other known resources, but also to an unknown one. This is from my colleague Graham Heinson at Adelaide. Map the mantle, find the large deposits. And as I just mentioned, Cam McQuaid gave an excellent rationale for why you'd want to do regional context studies. Australians are way ahead on this. They're doing this mapping at 55 kilometre station spacing right across Australia in their OSLAMP project. US Array covers about half of continental US. The Sinoprobe in China is covering about a third of China. South Africa is about to embark on regional coverage. I would like to suggest it's time for CanLAMP, or whatever you want to call it. This is a map of station density in Canada as of 2010, and a lot of those stations are mostly crustal probing. You can see there's a huge amount of Canada we know absolutely nothing about from an electrical perspective. Electrical methods are much quicker to install and get results back from, say, teleseismics. And so I think there's a lot more we could do. What is out there? We need to start petitioning the federal, provincial governments, and we need industry support. So in conclusion, I think MT's come a long way since the early days. There was a huge quantum leap in all aspects of MT in the late 80s, early 90s. It's a very viable choice for exploration, especially of deeper targets. But I think it's time for another quantum leap, and it has to be on all of these different areas. I think it would become much more adopted if it was cheaper to acquire and faster to process and model and invert. And if we don't go there, I'm just absolutely impressed about the how far other techniques have come. It's wonderful to listen to the talks at this conference about other geophysical techniques and how fast they're developing. And if MT doesn't develop, we're going to get left behind. Complacency is death. Thank you.
We have time for maybe one.
The difficulty with controlled source methods is that if you want to have full tensor information, you generally have to have a source that's 3 to 5 times the depth that you want to image away, and has to have then enough power that it comes back to you. Right, so you've got to have very quite a large source, and you've got to have two of them because you need to get tensor information. So it just makes a lot more sense to use anything below about 300 meters. It makes a lot more sense to look at natural source techniques and to modify your acquisition program so you're recording at night.